Hello everyone, welcome to the lecture series on ESP32. This is lecture 7 of module 2 FreeRTOS and ESP32. In this lecture, we will learn resource management. In FreeRTOS, we run multiple tasks. These tasks execute independently, but sometimes they need to use same thing. This same thing is what we call a resource. A resource is an entity that can be accessed by more than one execution context. The execution context is a task or an ISR. The resource can be a hardware peripheral, UART, LCD or SPI. Physically, there are only 3 UART, but each of the UART can be shared between tasks. Memory mapped registers. Memory mapped registers are also resource. These are hardware control registers mapped into memory. When we write to a register, we are controlling a hardware. If two tasks modify same register, data corruption can happen. Then, global or static variable. Global or static variable lie in shared memory. Every task can see them. If multiple tasks update the same global variable, we have a shared resource. In a multitasking system, multiple tasks execute seemingly at the same time. The scheduler can preempt a task at any instruction. If the task was using a shared resource, it may leave it in a partially updated state. Another task accessing it then can cause corruption, inconsistency, or a race condition. Now let us see hardware resource sharing. Suppose the UART hardware is shared between task A and task B. First, task A sends data temperature 25 degrees centigrade. But it could finish the sending, it got preempted. Here, it got preempted. And task B started sending data pressure 1.02 bar. So, the final print comes out to be temperature. So, it got preempted here and pressure 1.0. So, the resource is being shared by two tasks and this preemption is causing an inconsistency in the output. Now, let us see how even a simple bit update can fail in a multitasking system. So, we will see non-atomic operation in which read, modify and write is involved. Example, a LED control register. Initial value of LED control register is 0 on all the bits. Bit 0 controls the red LED, bit 1 controls the green LED. Task A turns on red LED by accessing this register. First, it reads the register value, then modify it. Before it could write, the task A got preempted. Task B turns on green LED. So it reads the register values. Since the task A was not able to write the value, still the register value is 0 on all the bits. Then it modifies the bit 1 for green LED to turn on. Then it completes by writing it to the register. Then again task E starts running and it writes the value that it was writing. So finally the LED control register has 1 at bit 0 only, the red LED. The green LED state got lost because the task E was preempted when it was about to write this value. It got preempted. So ultimately it wrote that value only. So the task B update is lost. So even a bit update operation which involves read, modify and write cycles, 3 steps. It is a non-atomic operation. After any one of the step, it can get preempted and the data can be lost. Now this problem is not limited to hardware registers. Even normal variable can behave like this. If a variable is larger than what the CPU can handle, suppose in a 16-bit architecture, a 32 variable is being updated, then it requires multiple steps. If context switch happens in between, the variable may end up in partially updated state. Same applies to structure or multi-step updates. Until now, we have seen how shared resources create problems. Now let us see how we can design function in a way that avoid these problems completely. A function is called reentrant if it does not depend on shared data. It uses only local variables which are stored on the task's own stack. In FreeRTOS, every task has its own stack. So if a function uses only local variable, each task gets its own private copy. That means no sharing. And if there is no sharing, there is no race condition. Thus we can tell if a function uses only stack variable, does not access global or static variable, and does not directly depend on shared hardware, then it is a reentrant function. Reentrancy does not protect shared data, it avoids shared data. Sometimes the sharing of resources is not avoidable. So in such cases, when sharing cannot be avoided, we use protection mechanism. The protection mechanisms are critical sections, scheduler suspension, binary semaphore, mutex, or gatekeeper tasks. All these we will see hands-on in the upcoming lectures. But still the best design principle is to avoid the sharing resources when possible. Design each resource to be owned by one task. Use queues for communication instead of shared variables. Good architecture reduces need for locking. So now let us see a real race condition in FreeRTOS. We will open Visual Studio Code. Then ESP IDF Explorer. Then New Project Wizard. ESP IDF version 6.0.0. Get started. Hello World program. Create project using template Hello World. Enter project directory. M2L7. Then project name module 2 lecture 7 part 1. Create project. Open project. Then close the older window. We will build the project so that the intelligence starts working. We will check whether the intelligence is working or not. IntelliSense is not working. So we will open settings, preferences, settings, extension, compile commands, inside build, the compile commands uses this file, compile command JSON file. We'll copy the name and put it here. Now save it. Now we will check the IntelliSense. Now it is working. We will delete the content of the file. Now here what we will do is we will make two tasks. Both tasks can call same function and both modify the same global variable. Here the global variable is the shared resource. So what we want is task A increments the global variable and then task B increments it and it alternatively increments a global variable, one after the other. So we are expecting a smooth sequence of 1, 2, 3, 4 like that. So let us see what happens when one of the tasks is preempted in between. It is not able to complete fully. It is reading and modifying the data but not writing it in the global variable. In such cases, data corruption can happen. So let us write the program. Include the header file stdio.h, then FreeRTOS.h, FreeRTOS.h, then tasks.h. Then we will make a global variable, global counter, and initialize it with 0. Then we will make the increment function. It won't take any parameter. Let us make a temporary variable. Temp assign global counter. Modify step. Then write back. Global variable equals temp. Now we will make two task entry functions. Task A, it will take void pointer as parameter. Infinite loop for the task entry function. Then it calls the increment counter function. Then we will print the global counter value. global counter. Then we will give a delay so that the task can preempt. It takes number of ticks as parameter. We will use PDMS to tick to convert milliseconds to tick. 100 milliseconds. Similarly, we will make task B. Task B. Here also task B. In the appmin function, we will create the two tasks. Now we will create the task. Xtask create pinned to core task entry function. Task entry function. Then descriptive name to the task. Task A. Then stack depth we will give 2 kilobytes. Then we won't pass any parameter to the task entry function. Then priority 1. We'll keep both tasks of same priority. Then we won't have any task handle. Then running on core 1. Create task B. Task entry function task B. Then here also task B. So now what we are expecting is task A and task B will be created. Task A will be running. It will call increment counter function, and in increment counter function, it will first read the global counter value, then modify it, then write it back. Then it will print the global counter value and it will go for a delay in the blob state. So task B will start execution. It will increment the counter value. It will read it, then modify it, then save it in the counter, global counter, and save it in the global counter. Then it will print it and then it will go to the blob state. So now task A will start execution. So like that it will continue. So we are expecting a print of task A1 and task B2 and task A3 and task B4 like that. Alternatively, both the tasks increment global counter to 1, 2, 3, 4 like that in sequence. So let us build the project. Then flash it. Select UART. Then monitor the output. We will pause the monitor. So this is the expected output. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It is going in sequence without break. So now let us create a situation in which before writing it back, the task gets preempted. To preempt the task, we will give a slight delay. vTaskDelay 1 tick. This will be a forced context switch. So now here what will happen? Task A will call the increment counter function. In increment counter function, it will read the global value, then modify it, but it won't write. It will be a forced switch. from task A to task B. So now what task B will see is it will see the older value and it will increment it and it will again get a switch. So now let us see how the print works. We will build it. We will flash it. Then monitor the output. We will pause the monitor. So now we are seeing task B1, then again task A is 1, task B prints 2, task A prints 2, task A prints 3, task B prints 3, task A prints 3. So it is getting the older value. The global value is a shared resource and it is causing this problem. The global counter, the shared resource, is being shared between the two tasks and one task increments and before writing it back, it gets preempted. So we are getting 2 times the same value is being printed by the two tasks. So in this demo, we saw a non-atomic operation in which read, modify and write is involved, and how if a task gets preempted before its execution is finished, it creates a corruption of data. So in the next lecture, we will see how to prevent this using the different protection methods. So that's all from this lecture. See you in the next lecture. Thank you.